Hello, everyone, and welcome to the Switch Statement Podcast. It's a podcast for investigations into miscellaneous tech topics.
This is our 8th episode on Gödel, Escher, Bach by Douglas Hofstadter.
Hey, John, how you doing?
Hey, Matt, I'm doing really well. How are you?
I am doing all right. This is, I think this chapter might be a little rough for people. It's funny because I think there's going to be this bimodal distribution of enjoyments of this chapter.
Yeah. I mean, for me at least, I think this is going to be something that's difficult for me because I'm a programmer. I've programmed all my life. And there's a lot in this book that is like programming adjacent. And I struggle to break out of just thinking about these concepts through a programming lens, which, I think there's a lot of value in thinking of them that way. But I think they're also like larger concepts than just that. So that's
this one I will say he is the most like directly, I'm just giving you the programmer. I'm trying to get you to like a programmer's intuition of recursion.
Yeah. There's a point in the chapter that straight up had like that diagram that SQL languages will have?
Yes.
It's like, so, and maybe we'll get to this, but there's a point in the chapter that literally had that diagram that I never realized that, well, I guess this is probably so obvious, so it's dumb to say, but like that has its roots in linguistics where
right.
It's, you're kind of saying like, oh, you have this part of speech, what could possibly come next? It sort of branches from there, and then what could possibly come next from that branches. So I don't know. The minute I saw that diagram, I got flashbacks from learning SQL.
This is one thing that is really cool about taking a computer science course and then going back and looking at linguistics.
Yeah.
Because you do realize how there's a reason they call them programming languages. I feel like you don't think about it that way, but when you're doing this like consumption of token or like this conceptual like hierarchy of expressions and sentences and clauses and what have you, you realize how much DNA they share, so to speak.
Yeah, totally.
But yeah, so this is chapter 5 of the book, and it is called Recursive Structures and Processes. So I mean, as we kind of alluded to, we're talking about recursion.
As with the other chapters, it kicks off with this dialogue between our friends Achilles and the tortoise. And there's this additional character named Hexachlorophene J. Goodfortune, which I like. But anyway, I actually did not read this whole dialogue because it was very long and I really wanted to get into the content of the chapter. But I read a little bit of it, and structurally, it was recursive. Like the dialogue itself, hexachlorophene kind of threw them in this torment like world. That's such a weird way of describing that. But anyway, they just kept going into like sub-worlds. And there were some interesting things about the dialogue that he actually discusses a little bit later in the chapter.
Well, the thing I was going to say about this dialogue is I think I know where Christopher Nolan got the idea for Inception.
Yep.
Because literally in this book, they have a diagram of the, of this dialogue.
Yeah.
And it looks very similar to those like explainer diagrams about Inception. So I don't know, because it does involve, and it's funny because I think if a person has any awareness of recursion at all, it's like the Drost effect. I don't know if you've heard of that.
Drost effect? No.
Or Drost. The Drost effect or Drost effect, it's Droste. And it refers to, it's a picture of so the product is hot chocolate, I think. But the product picture is a woman holding a box with a picture of the hot chocolate, and she's on it. So it's this recursively nested. So I think people are maybe familiar with these like infinitely self-similar recursion where it just goes on forever. And that's not actually what Douglas Hofstadter is talking about. He's talking more about these like recursion, because you need to have a base case in order to do something useful with recursion.
Yeah, bottoming out.
Bottoming out.
Yeah.
But it's not. So I guess all of this is a long way of just saying that the stories are not very self-similar, but they do talk about like pushing and popping. I don't know if you got to this. Like, there are these like two serums or whatever, and then there's like it was push. Oh, I'm forgetting what it was pop tonic and push soda or something like that. And it gave you the ability to push yourself into a picture. So, but obviously he's using those terms very intentionally to refer to like pushing stack frames onto the stack.
Right. Yeah. Very, very, programmy, like alluding to a very programming concept of a stack frame, which gets pushed every time you call a function. He mentioned an interesting thing about resolving like recursive structures that I found fascinating, just because my personality, and this is probably because I'm a programmer and have been doing it for so long, but if there's some sort of recursive structure and it doesn't like pop all the way to the top, let's say Inception had gone down into 3 subworlds, but had only popped back up 2 subworlds by the end of the film, like that would have been like very infuriating to me. But he talks about how some people aren't as aware of that type of thing. Like, again, I didn't read the dialogue, but he mentions how in the dialogue, like one of the characters is super concerned that they haven't like popped all the way back to the beginning, but the other one is just kind of blissfully unaware. I thought that was funny.
Yeah. There was one very other very small, or it was actually like a major reference, but I think it was so in this story he talks about how they're on this Ferris wheel. So Achilles and the tortoise, these are our kind of classic characters that we keep on seeing. And so they're on a Ferris wheel, and there's a guy with a hook that is like flying over him with a helicopter, and they grab onto it. And I think with that story, he's referencing this this term. There's this book called Darwin's Dangerous Idea by Daniel Dennett, which, man, there's a lot of these.
A lot of alliteration there, yeah.
This is a real book, by the way. It's not like made up for some, it sounds fake, but he says, evolutionary biologists who are not strict Darwinians hold out some hope for a metaphysical skyhook to explain the existence of things like human consciousness. And I think that is basically just because the idea being that like you just want some sort of magical thing that's going to come along and like solve this problem for you. And so that might be a tenuous relationship, but or maybe I'm grasping at straws there. But
I don't know. That's very interesting, though.
But I've heard this in psychology or philosophy, where it's like you refer to a skyhook as something that is kind of like, it's like the question mark and then like profit. It's basically, if you say step 1, like collect all the underwear. Step 2, question mark. Step 3, profit. Like that question mark is the skyhook, where you're just trying to like paper over everything.
I just thought he was referring to Kareem Abdul-Jabbar's cheat code in basketball, just skyhooking all the time.
Yeah. I mean, it was hard to Google for because of that.
He mentions an interesting thing about music that I actually was not really aware of. Like, I'm pretty familiar with music and music structure and some music theory. But he mentions how a lot of times in music, there's this notion of like you're pushing keys, but then you have to sort of pop back through the keys that you pushed, which I'm much more familiar with progressions where the progression itself might repeat. Like there's 2, 5, 7, which is like a jazz, blues, rock progression. But it's not like you, and those represent keys in a scale, by the way. But it's not like you go 2-5-7-5-2.
Yeah.
I mean, sometimes you might, but I don't think there's some hard and fast rule that you have to do that. But he mentions Little Harmonic Labyrinth, which is a pretty cool Bach piece that I guess exemplifies this. I listened to it. I couldn't really, I mean, I could hear key changes, but I couldn't really hear that it was like popping back through the keys. But I thought this was interesting. I feel like I'm going to learn a little bit about music theory reading this book because he keeps mentioning these things.
Oh, interesting. So that it was also the name. So Little Harmonic Labyrinth is both the name of the
Bach piece and
Bach
the
piece
dialogue.
Oh, fine. Yeah, I guess I'm not surprised that he did that.
It's a cool name. It's just like I don't know. It's a fun little piece of music. I can just imagine Bach like titling it that.
Yeah.
It's kind of cute. Yeah.
This is so funny because I don't know, like you're saying, I think of key. Maybe I'm thinking more of chord progressions, but like obviously for chord progressions, I think of them as a cycle. Where you're just kind of like looping through.
Right.
I feel like key changes I don't have as good a framework for, because I feel like my conception of a key change is you just change the key like once and then that's it. You don't necessarily change back, and there's not necessarily even two key changes.
Yeah, well, right, exactly. That's kind of I just am not really aware of any rules with key changes. It's like you do it to, sometimes you'll key change to a dramatically different key in order to completely change the tone of the music. Sometimes you'll key change like one key up. It sort of gives it this like lifting feeling. Sometimes you'll key change from minor to major, blah, blah, blah. So there's all these different things you can do with key changes, but it sounds like he's mentioning like a specific form of music where it's almost like recursive in the way that it key changes, which I thought was pretty cool.
Which I could totally see that, where it's like you have a key change. Like if we're just talking about the simplest case, where it's like you have a key change for a little while and then that resolves back.
Yeah. Totally. I can totally imagine this being like a return to, because sometimes key changes can make you feel like a little off balance at first. So it's sort of this way of like, ratcheting up the tension, making you feel a little bit more off balance, but then sort of bringing you back home. And I can imagine that, being very satisfying.
One thing I would say about recursion in music is, I don't make a lot of music. I got this, kind of into a little rabbit hole a little while back trying to like make some music. And one of the things that I tried was kind of this like recursive subsectioning of music, of the song, where it's like, and I actually used like the golden ratio, where it's like, okay, I have, there's the first part of the song and then the last part of the song. And then their lengths are roughly like the golden ratio. And then I split both of those up into like little chunks that are in the golden ratio, and then each one of them have their own little like, so maybe you would have like a key change on the second bit of the whole song.
Oh, interesting.
But so, and different things are changing at these like separation points, but there's always like, changes in the music are always like kind of falling on these golden ratio separations.
Hey, dude, maybe you found some mystical, secret code of music.
Maybe. That was Miami. So
nice. Well, that was a cool song. We should like play it in this podcast.
Yeah, I'll put like a 5-second clip. All right. Or maybe I'll just have it go for the outro of this episode. I'll do Miami.
Let's do that, dude. I mean, I really like that piece, so we should definitely throw it on. He mentions a very funny thing. So I have a limited knowledge of German. I took German in high school. Again, very limited knowledge. But he mentions this interesting quirk about the German language. I think a lot of languages have this, where a lot of times in German, you'll take the main verb of the sentence and you'll sort of put it at the end.
Yeah.
And he gives a joke. I didn't write down the exact contents of the joke, but it's like, some German professor is speaking, and you basically have to wait. The professor goes on and on and on, and you have to wait until the very end, and then he just spits out a bunch of verbs, and then you finally understand what he's saying. And I've definitely observed this in German. Like I remember, there's a sentence like I have slept or something would be like, ich habe schlafen. I'm probably getting the conjugation wrong, but you can put all these phrases in there. Like I have slept in my bed would be like ich habe ins Bett schlafen. So if you combine all of these phrases or add all of these clauses to the sentence, you can have this like arbitrarily long sentence. I slept in bed with my dogs comfortably or something, where sleep goes at the very end of the sentence. So you don't even know what's happening until they say schlafen. And I just thought that was a funny example to throw out.
Yeah, I'm so glad you're bringing this up. Like I looked around for a good example of like how these could stack recursively. But maybe the way that it works is like if your dog is doing something, you know what I mean? Like can your dog be like, if your dog is eating, it's like I slept with my eating dog. It's like I dog eating slept, I'm grasping at straws here, but I guess that's maybe how you could stack those.
Maybe. Yeah, it's interesting because I wasn't as familiar with like stacking a bunch of verbs at the end. I'm much more familiar with the thing where it's like, you have a main sentence, but you can just kind of arbitrarily throw all of these clauses in the sentence, and the verb, which, a verb is pretty important to a sentence. It's like until you've heard the verb, you don't really know what it means. And, Germans put that verb at the end in a lot of cases. But yeah, maybe. I wonder, I should figure out how to say I slept in bed with my dog who was eating.
Yeah. And then you could go even further, like eating a chicken who was singing, or, and so maybe that's how you stack the...
But the whole reason he was throwing out this joke was because he was talking about recursive transition networks, which this actually goes back all the way to me bringing up SQL diagrams. So recursive transition networks are basically these diagrams that show how a grammatical structure can, or shows how, various sentences can be created given some grammatical structure. So like with SQL, you start with select, meaning you're like getting data from some source. And then you mention like what you're actually selecting. Like, let's say you have a table of employees or something. You might say select name from employees. But also in SQL, you can do things like selecting from a query itself.
Right.
So you could say like, select name from, and then have another select.
Right.
So you're literally selecting from the results of some other select. So there's some cool recursive transition network diagrams for SQL where after the from, select star from, it sort of loops back to select. And that diagram shows that you can sort of represent these arbitrarily complex select statements.
I feel like once that clicks for someone who's learning computer science, that's really when it starts to feel like a magic trick.
Oh, yeah. Yeah. As any programmer who's listening to the show knows, recursion is truly powerful. Like it's just, as a concept in programming, it's so much better at representing certain types of problems. Like anything that's a tree problem or like a graph traversal. Obviously you can do these algorithms iteratively. You can sort of put everything in a stack manually. But if you get the right sort of representation of the problem, and sometimes that's recursive, the solution can feel so much more elegant, so much easier to maintain and read. And those things are very, very important when you're talking like large code bases with lots of engineers working on them.
Yeah. But what I was going to say is like if we're thinking about the example of the SQL query, like what feels so confusing about it is like you'll be reading like, okay, this is the structure of a SQL query. And then in the middle of it, it'll say like, oh, you can have a query in here. Like in the definition of how you can structure a query, you will have a query itself. And that's when your brain is breaking. You're like, wait a minute, we haven't even finished defining what a query is. How can you be referencing it in the definition?
Oh, yeah.
And, and I don't know, like, I just want to make sure that and I might even like, I don't know, I might cut this and put it back earlier, but just, I'm not sure that we like took a step back and clearly defined like what recursion is. I feel like we've been coming at it from a couple of different sides, but like at its core, recursion really is, I mean, I think of recursion as self-reference, where, for programming, it's like you are referencing something within itself. And like if we're thinking about the SQL query, you say, oh, well, like you can actually reference what a query is within the definition of a query. Right. And so just as like a little aside about like, if you've never heard of recursion before, like it's basically that, where you're saying you're kind of using the definition of the structure itself within itself. And like, that's when you get to do all these like powerful things, because otherwise, like I'm thinking of something like JSON. JSON is obviously like this recursively defined structure, and JSON is just a way to store data for the web. And I mean, it's very similar to SQL, but you can have JSON objects that are kind of nested within other JSON objects. Mm-hmm. And then like if you wanted to do that, like you would just have to manually like define the structure the whole way down, like as and then you would have some like depth limit if you wanted to just like never have self-reference. And it's just like, I don't know, it's just fundamentally limiting, I think, in a way that like recursion just kind of frees you from that.
Yeah.
So
yeah. No, I would even go so far as to say some problems are like, they're not impossible, but they just become extremely difficult without recursion. But with recursion, they become trivial. The one that I really like, I remember in college, I was so dumb at programming at first, and I remember programming a binary tree, which is basically a data structure where you have a node, and the node has a left and right pointer that both point to nodes. Yeah. So it's recursive. It's a recursive data structure where a node points to two subnodes. And our teacher was like, okay, how do you find the height of a binary tree? And you think to yourself, like if you visualize a tree, like if you just see a tree in your mind and it's got a node at the top, splits into two nodes, those both split into two nodes, you can sort of see the height. It seems like this super duper simple concept.
Yeah.
But when you're writing that in code and all you have is like, a node, like what code do you write in order to figure out the height of a tree? And it turns out it is an amazing recursive function. Still one of my favorite recursive functions because of this college experience where I felt like it was finally clicking for me, where in order to calculate the height of any given node, you just get the tallest height out of your children. And then, and basically you add, well, okay, so actually let's back up just 1 second and talk about bottoming out, which I'm realizing is the next note I have. So in any recursive structure, there's this notion of bottoming out, where, like we were talking about before, in SQL, you can select from a select itself, but you can't like infinitely do that. You can't select from a select, from a select, from a select, from a select, from a select. There has to be a point where you're selecting from some root source. Otherwise, it just goes on infinitely and breaks, right?
Yeah.
So that's kind of what
your computer runs out of memory. Like you said, like the reason why you can't do it forever is like kind of for this mundane reason that like there's a limited number of atoms in the universe. It's like at some point like you got to end the query. That being said, like there's nothing in the recursive structure that's going to stop you from doing that. Like you could go on all day long.
Oh yeah, you can have all sorts of stack overflows in your code. But generally speaking, if you have a recursive algorithm in code, you might have like a little bit of code at the very top of your recursive function that says like, if some condition is true, then just return something immediately. Like don't even recurse. So in this example of this height on a binary tree, basically if you have no children, like if your left pointer is null and your right pointer is null, then you just return 1 because that's the height of a tree with no children. So then the recursive function becomes, just give me the 2 heights of my children, pick the larger one. And so it's this like utterly trivial function once you write it down. But it's, I think it just sort of like exemplifies this elegance of recursion because you've sort of done this hard thing, but you've written like 2 lines of code. Right.
And actually just very quickly, getting back to, like we said, okay, you can't write an infinite SQL statement, like it has to end somewhere. The problem with when you're writing like a recursive function is like there is nothing to stop you but time from writing a function that is going to recurse infinitely if you don't have that bottoming out. Like let's say you forget to check for the case when like both of your children are null, then like you might just keep on looping forever.
Exactly. And often in a program, you can have these scenarios where function A calls function B, but then in the running of function B, you're also calling function A, which is sort of this other form of recursion where things call each other, and those cycles can be arbitrarily complicated. You can have function A calling B, calling C, calling D, which calls back into A, and so this is why, as a programmer, you need to be very careful about representing those bottoming out scenarios. Because you can have arbitrarily complicated code, and you need to make sure that there's not some weird edge case that forms an infinite loop.
This is why I never understand how our question parsing works in matchops.
I am so amazed that has not broken in a million ways. It does work.
Yeah.
He talks about diagram G, which I thought was very interesting.
Ooh, this one I don't know if I read so closely about diagram G.
Yeah, I mean, I should have written down a picture of the diagram itself, but it's basically a diagram. You can think of it as sort of like an upside down tree with 2, it's an upside down binary tree with like a left and a right. And
in a way, it's kind of like a correct way tree. You know what I mean? It looks like a real tree.
Yeah, it looks. That's actually, yeah. I forget that most trees are right side up.
Branch up.
As a programmer, I think of all of my trees as being upside down. But anyway, the left node has just a single node, but the right node has like a copy of itself, which is again like a tree where the left node has a single node and the right node has a copy of itself. So it's this recursive tree structure. But you realize that if you're building this tree structure by iterating, like let's say you start with just one single rendition of this, and then at each node you're adding itself. This is very hard to describe without a diagram. But in any case, I'm just going to like not bury the lead and say that it creates the Fibonacci sequence. So right. if you're basically counting all of the leaf nodes, you're going to get 1, 1, 2, 3, 5, 8, 13, which is kind of cool. And you can see it very easily in the diagram, and I'm not doing a very good job of describing the diagram.
I mean, this gets back to what he says about isomorphisms. Like, I don't know, it's just one of those places where you kind of learn that like 2 things are actually the same thing, even though like their trappings are different.
Yeah, one thing that I thought about when I was reading this is you start to see why certain things arise in nature. Like I remember hearing this, like you just talked about the golden ratio. And, people talk about how the golden ratio happens in nature all the time. And I think when you first learn that fact, it's just completely mind-blowing. And I think it is still sort of mind-blowing. But that is a number that's just intrinsically linked to recursion.
Yeah.
And the Fibonacci sequence, again, is intrinsically linked to recursion. So if you're seeing the Fibonacci sequence in nature, it probably means that you have some, sort of recursive structure happening. Like two entities form another entity, and then those three together form two more. So it's very like, once you see the pattern, you can sort of, it becomes a lot more rational that these numbers would just appear in nature all the time.
Did you make that pun on purpose?
No, but I'm happy with it.
Yeah, and so isn't it there's some estimation of like the nth Fibonacci number that uses the golden ratio, right? Isn't it? It's something like phi to the n or something is like the n, approximation of the nth Fibonacci number or something like that.
Yeah, something like that. I feel like there might be an E in there. I feel like there's always an E in there.
Yeah. So we have he gives us this very beautiful but like bewildering graph. He defines a function called int x.
Yes.
And the outcome of this function is a chart. I mean, it's like, to produce it, you're just doing this kind of conventional, like, okay, you go from 0 to 1, and then you just plot, you compute the value of int x at every point along the way. But what's so remarkable about it is you get this like almost like seesawing effect where it's going to be impossible for me to describe. It really doesn't look like anything else I've ever seen. Like, I guess the closest way to say it, it's like these alternating like parentheses back and forth along the like negative, basically an inverse, a perfectly inverse correlated line. So like a line starting from the top left down to the bottom right that's made out of recursive parentheses. Yeah,
and this was really cool. I mean, people should just look up the graph because it looks very beautiful. And I think it's also an example. There's these cool things that you learn of in programming, or at least that's where I learned of them. I'm sure they talk about them in a lot of other disciplines. But they're called fractals, where basically there's a mathematical representation of an image or a graph, and the more you zoom in on any part of that image or graph, it just keeps creating itself. So you can kind of like infinitely zoom in on any position in this image, and it will just keep creating itself. And it's really mind-boggling, when you see one. But it's also, they're typically like, well, I don't want to say typically, but a lot of times they're just very easy to describe with math. Like it'll just be a formula with like two variables. And so it's just this cool thing that can arise with these recursive structures.
Yeah. I think what's funny about recursive structures is they're all at once. They're like this mix of novelty and similarity, like at the same time. Because I think I've heard something, I think I watched a Vsauce video where he talked about like music and about how human brains kind of like they're most interested in this like sweet spot of complexity, where it's like if you have just white noise, which is like infinite complexity, it's going to be like, I don't know, it's so complex that you can't find any patterns in it at all. Your brain is like, I'm just discarding this. There's nothing here. Yeah. And then if it's like just a line, you're like, okay, well, whatever. Like, I don't care. But like recursion is kind of this beautiful balance where it's like, I feel like some people almost get like entranced by recursion because you can just keep on going and it's never exactly the same, but it does continue to be very similar, which I think is very visually satisfying. Yeah. And then, that's kind of evidenced by how many like 10-hour Mandelbrot set zooms there are on YouTube.
Yeah. Have you ever just watched an entire one of those?
Oh, yeah.
He talks about Feynman diagrams, which are these diagrams that I guess describe the behavior of subatomic particles. I'm going to be honest, this part like really went over my head, but it was very beautiful. I guess, quantum mechanics describes there's just 25 particles or so and 4 forces, and basically everything in our universe emerges from just those 25 particles and 4 forces. So I guess these Feynman diagrams are ways of representing those interactions. And they just look really cool. Like, I get, this is like, I feel like a theme with Feynman, like stuff that he works on. I feel like he was the guy that would always just work on like the fun, cool thing, when everyone else is like getting into the nitty gritty.
Yeah. He had this very cool, like, shorthand for sine, cosine, and tangent of something, where he would basically just take each one of those letters and then just extend the top bar over what they over the rest of the expression, which I always thought was like this very beautiful, like he kind of had an artistic eye, I think.
Yeah. Oh yeah, he was a guy who saw the beauty. I think a lot of what drew him to science was the beauty that was there.
Yeah.
Just having read, like, there's a great book, I think it's called Seriously, Mr. Feynman, You Must Be Joking or something. It's got a weird title.
Yeah.
But it's sort of like a biography, autobiography. Really, really good book, really fun read. But you can sort of tell that he's attracted to the beauty of things. He's not this like hyper analytical, like, I mean, he's obviously hyper analytical. He was a genius, but I think that, I think he would think of himself as like a creative person, like with a lot of artistry in what he does.
Yeah. And I think he also just had a lot of respect for, or like just appreciation of where students were coming from in terms of like doing their explanations. Like, I think it's way too easy to just get caught up in all the details, but like, I think the way he taught was always like, I don't know, meeting the student like where they're at. So
yeah, great educator, great science communicator. If there's a lot of YouTube videos actually of him describing like fairly complex things, and he just, like you're saying, he approaches his scientific descriptions very well.
So this, I didn't fully understand how this tied back to recursion, but I guess the idea is that, like, similar to what we were saying before, where you can have a node, or like you can have a structure in this Feynman diagram, and then there's some set of possible like transitions that node can make to other nodes.
Yeah,
that can contain the original node. Is that kind of the idea?
Yeah, I think so. I think it was kind of like those recursive transition networks that we talked about earlier. And I also feel like there was feel free to correct me if I'm wrong, but I feel like Hofstadter mentioned how there was only a finite number of these Feynman diagrams. And which makes sense if you think about it. Like, there's only so many subatomic particles, and they can only do so many things. And I think with these, a lot of people who study quantum mechanics will just kind of know all of these Feynman diagrams by heart, and they'll basically be able to take like an atomic system and sort of think about those Feynman diagrams and apply it to that atomic system.
Yeah. Well, yeah, I want to learn the rules of this grammar, because he has one here which is like just very hard to understand what's going on. But like,
yeah, dude. I looked at that one for a while and I was just like, nope.
Yeah.
Shortly after this, he mentions Rachmaninoff's Second Symphony, which I just wanted to shout that out because I think Rachmaninoff is in my top 5 musicians of all time. He wrote, there was this period of music it's easily one of my favorite periods where, like the Romantic period was sort of in full swing. This is sort of the Chopin period where music just got very melodramatic, like sort of the classical period was characterized by, a lot of this like beautiful, sort of like Beethoven, where it's like these beautiful, simple, powerful, melodies and orchestral arrangements. And I feel like it led into this like impressionistic romantic period, which just had these like very dramatic pieces of music, where you'd have these cadenzas that were just like, and a cadenza is a part where like a soloist sort of takes over and just does something completely insane. And Rachmaninoff has these piano concertos that I feel are kind of squarely in this, historical period in music, where the pianist is just playing this like incredibly elaborate, very technically difficult. His pieces are famous for just being incredibly technically difficult, but very beautiful, very, kind of over the top, almost like schmaltzy. And so anyway, I love Rachmaninoff's music. So it was cool to see him mention the Second Symphony, which I guess has some sort of recursive structure. Again, I was unaware of, I've heard the Second Symphony, dozens of times. I wasn't aware that it was recursive. So
yeah, I mean, he's kind of getting, like, I think he's being a little bit loose with the term recursion here. I mean, he's talking about like modularity and breaking things down into these like sub-components. And I think he's almost more like viewing at it through that lens, where it's like there's these chunks that can be kind of like recomposed.
I think you're right. And I think a lot of folks who might be reading this who don't know music theory are probably surprised to learn that there's a significant amount of like structure and rules that govern music.
Right.
Or I shouldn't say that govern music, but like, most music that we're aware of is written within these structures and, keys, well-known chord progressions. And so I think that he's like you're saying, I think he's just kind of alluding to a lot of those musical structures and just using them as like yet another lens through which to view these concepts.
Well, that's a really good point. Like, for example, the canon, I never realized, like, the canon is a piece of music with a tremendous amount of structure to it and rules governing it. Like, there's, and maybe, this ties back to the, the language or what have you. Like, once you start writing it, you become quite constrained. There's only a certain number of possible, like, almost solutions to the constraints laid out. And he references in earlier chapters about how like they would leave some of it out because it was just defined by the prior part of the canon.
Yeah.
So
totally.
There was one point, just going back very quickly, for anyone who has done a little bit of programming, like, you'll very quickly run into loops. I feel like it's like the first thing, or like maybe after variables, you just go right into loops.
Yeah,
and
flow control.
It's easy to think of loops as just this innate thing, but we actually worked on a programming language together. And what's funny is you realize that implementing looping via recursion is actually like easier and just actually happens earlier than writing a loop.
Yeah.
And it's just funny because we just discovered that accidentally, but like this is how he structures the chapter. He talks about recursion first, and then he talks about loops kind of downstream from that. And I think from like a conceptual level, that's actually how it works. It's like a loop is actually this more complex construct than recursion.
Yeah. Oh man, I'm so glad you're bringing this up, because there's so much of programming with loops that I think is just completely fascinating. Like, there's a language that I really love called Scala, and they represent their lists as a head and a tail, where the head is just the first item in the list and the tail is like the rest of the list. And when you first see this, and there's other languages that represent their list that way too, but when you first see this, if you're coming from like Java or C++, you're like, what the hell? Like, this is crazy. But you quickly realize that representing your lists that way enables you to do these like recursive comprehensions with your list, where you can say okay, I want to do this thing with my head, and then, do this other thing with the rest of the list, which might be to just do that thing over and over again with the rest of the list. So you can write this code very easily where, let's say you have a list of numbers and you want to like square all of them. You can, in Scala, you can just say something like, take this list and map this function over the whole thing. And because their lists are represented in that way, they can just kind of take the operation, apply it to the head, and then pass that operation down the tail.
Right.
And you just get this new list back, that's all your numbers squared. And yeah, like you're saying, it's like that way of representing your list that facilitates these recursive algorithms like maps and folds and stuff. It enables you to do a lot of, very cool, elegant things in your code that you really can't do otherwise.
Yeah, it is funny because, and I guess like if you're kind of, I don't know, looking more at the structure of that, it's like you have something that takes a list, and then once you can grab the first thing and then split it off from the rest, like it just lends itself very neatly to, and I mean, I'm kind of repeating what you're saying, but like now you have the rest of the list, and then you can obviously just pass that back into the original function because it took a list in the first place.
Yes, exactly. Yeah.
And so, yeah, that feels like a very powerful paradigm.
Yeah. He mentions one of my favorite algorithms of all time, which is Minimax.
Yes.
Which is this, famous artificial intelligence algorithm. And this is more old school artificial intelligence, where, the entirety of the intelligence is encoded within the lines of code. But basically, maybe we can give a quick description of how Minimax works. Like, let's say you're playing a game like chess. If you're trying to think of the best move that you can make, one way of thinking about that is to pick the move that gives your opponent the worst options. So, for example, it's going to be hard to think of an example, but let's say I pick a move that gives you the worst options. I know that you're going to pick the best option out of those options. And then that if you pick one of those options, I'm going to pick the best options that I'm with, or that I'm left with. So Minimax is this algorithm that assumes that your opponent is always going to pick the best option available to him. So you're basically picking the option that minimizes his best option, which is kind of where the algorithm gets its names. Like say we represent a chess game as an integer score, where like in chess, there's a concept called material, which is basically the pieces that you have on the board. And one naive way of calculating like the value of a position is to just take the quantity of material that I have and subtract the quantity of material that you have. So if you have more material than I have, it'll be a negative number, which means that you're doing better. If I have more material than you, it'll be a positive number, which means I'm doing better. So my goal is to leave you with options that are higher value, and your goal is to leave me with options that are lower value.
Yeah. And then you're saying you're using those assumptions to explore the space, because like even if you've computed my best possible move given your options, you don't know that that's true. So I guess you need to do some searching where you're like, okay, well, these are the 5 moves that I think he might possibly do.
Yeah. Well, and
go for it.
Well, that gets into why chess AIs are so interesting. because chess, as most people know, has this explosive, permutations of possible moves you can make. I think by like the fifth chess move, there's like 10 billion combinations or something. So you obviously can't, in a computer algorithm, you can't calculate every single option, which leads you to what is referred to as a heuristic function.
Yeah.
Where you basically take the state of a chessboard and you try to calculate this score. Like I was saying earlier, an integer score. And, a dumb way to calculate it would be to use material. A smarter way to calculate it might take into account what's commonly referred to as tactics in chess. Like, let's say you have a knight, and a knight moves with an L shape. If you can move a knight into a position where it's attacking two pieces at the same time, that's called a fork. Meaning your opponent can only move one of those pieces away, meaning you take the other one. So a fork is a tactic. And so another way that you might score a chessboard in your heuristic function is to take into account forks.
Yeah.
And so chess AIs are actually a really fun thing to write if you're a programmer, because you sort of have to be smart about this heuristic function and think about forks and pins and alignments and things like that, and sort of assign values to these things that might change over time as the game progresses.
Now the new techniques, and maybe this is like getting too deep into chess, but the new techniques like Alpha Zero, are they minimaxing? And they're just like using a better like evaluation function that's learned, or are they not even minimaxing at all? They could just take the board state and directly translate that.
That's a good question. I mean, I know they're using a machine learning model where presumably they're plugging in the board state and getting some sort of score. I would imagine that there would still be value in mini-maxing, even with that. But yeah, I actually don't know how those newer chess algorithms work. It's pretty cool.
Well, this is one thing that's really cool about the minimax is like you have a black box, at least for chess, right? You have a black box function which consumes the board state and it tells you, well, I guess, is that true though? Because that's funny because like the quality of the board is almost like, and this is where the recursion comes in. It's like a downstream effect of like because I guess at some point you need to have something that says how good is this board position for each player, right?
Yeah.
Right.
Yeah. But that's, I mean, I think like you're getting at like in chess, that's often wrong. Like there's a thing in chess called a sacrifice, which like, let's say I give you my queen, but like the queen is the most valuable piece in the game. But the reason I'm giving you my queen is because there's this combination that I'm about to do that has a bunch of forcing moves. You take my queen and then I put you in check 7 times and then I win the game with checkmate. So there's a lot of, you'll actually see if you look at like a stockfish evaluation of a position, is the evaluation will actually go up and down depending on how deep the stockfish algorithm has run, which by the way, stockfish is a world famous chess AI. It's the most powerful chess AI. So yeah, you'll see that like that heuristic function alone does not tell the whole story. You sort of require this depth to be able to know like, is this a short-term loss of value based on some longer-term, sort of strategic gain? And that's what the depth of the minimax will tell you. And that's why there's a lot of research and work done to try to minimize the number of nodes that you're actually looking at, so that you can increase that depth. Like, so every node that you can sort of eliminate from contention has a huge amount of value, because nodes that are high up in the tree represent like thousands of nodes that are lower in the tree that you need to look at. So if you can prune those nodes early, that's very advantageous.
Yeah, but it seems like like you have the risk that you're potentially cutting yourself off from some amazing move that this opens up
Yeah, totally.
downstream. So like, I don't know. It seems, and that's why it's interesting, an interesting problem, I think.
It's totally interesting. I actually watch these chess videos sometimes that'll talk about like AIs playing against AIs, and there are often these moves that make no sense to a human being. You know, it'll just be like they'll just like give away a bishop like early in the game or something, and it's like, what the hell is going on? But then like 20 moves later, they'll have the opponent in this position where they just can't move any of their pieces. And it's sort of this example of like, you know, you're making a move that looks really terrible, but in actuality, you know, there's this very long-term strategy where that move, it puts you in a better position.
Yeah.
And it's interesting. It's interesting to see the evolution of like chess AIs and how they just, because it's something that you can very easily just like pit the new version against the old version and like make sure it wins every time.
Yeah.
So it's this type of thing that is just getting better and better. You know, it's very easy to like not get worse. So yeah, it's kind of crazy.
Man. Well, there was one more thing that I did want to talk about, or just like this is just like an amusement.
Yeah.
Had you heard of Hofstadter's law before?
No.
Hofstadter's law is it always takes longer than you expect, even when you take into account Hofstadter's law.
Yeah. It's a very programmery thing.
And it's so funny because I feel like I've heard this forever. Like I don't know, when I heard this, probably 10 years ago. But I did not realize that this is the Hofstadter referenced in Hofstadter's law.
Yeah. So. Yeah, and like, to be clear, I have heard that before, but I just don't, it doesn't always reference Hofstadter. Like, it often just says, like, you know, things take longer than you think they will, even when you take this into account. So I feel like he's not getting his due credit.
Yeah. But that's all I had. Man, this one was probably this one was dense.
A little chunky. There was actually one last concept that I did want to mention.
Yeah.
He briefly discussed programs that can modify themselves at the end of this chapter, which, you know, this is one of those concepts that, you know, is very, very powerful. I mean, you can imagine if a program could improve itself, like going back to these chess AI situations, like if a chess AI could somehow tell that there was this weakness in the heuristic function and actually fix that weakness itself, like obviously that would be tremendously powerful because the thing would just get better and better over time. And he mentions how this ability, which he also refers to as tangled recursion, which I thought was a cool way to reference it. But he refers to this ability as the heart of intelligence, which it's yet another thing in this book where, you know, it's 2024. We have Chat GPT 4.0, where you can literally talk to a computer and it talks back to you like a human being. And this book was written in the 70s?
Yeah, I think so.
And he's talking about, you know, programs that can modify themselves and that being the heart of intelligence. And I just think there's going to be a lot of references like this in the book where he's, you know, just talking about these things that are very applicable to today.
Yeah, man, this book feels so prescient. Like, I mean, this is something that I had always thought about. Like, I mean, and my conception of it is like not what it looked. I imagined a program that could, like, you know, I was writing C and I was like, okay, well, can it like output C and like compile that and then run that? Yeah. And it's funny because the first person that I talked to about that, he was like, well, that sounds like malware. Like, that's kind of the main reason why people do self-modifying code. And then I was like, oh, okay, well, maybe. But I don't know. I mean, obviously it looks completely different, but
Well, it's funny too, because that's almost more complicated than backpropagation, which is one of the primary principles that make LLMs so powerful.
Right. Well, it's also probably just worse. I can only imagine that like it's just it's much harder and not as good. But yeah. I mean, someone's gonna come along and stick like program compilation into like the loop of one of these AIs. It's probably already happening.
People are already doing it for sure.
And yeah, Skynet's going to be here before long.
Yep. Maybe we can end on that pleasant note.
Yeah. All right. No, I'm a techno optimist. I think it's going to be utopia.
Future looks bright.
All right. Well, I will see you next time, John.
See you next time.